Good day, I'm Norman Wildberger. In this very interesting and important lecture, I'm going to introduce, first of all, a modern variant of a very classical and famous result, the formula of Brahmagupta for the area of a cyclic quadrilateral. We're going to combine Brahmagupta's formula with a much more recent formula due to Robbins, discovered around 1994. And we're going to combine these two, but reformulate the whole framework in a rational way. So this is evidence that by thinking rationally and logically about basic fundamental geometrical things, we can actually discover new ways of formulating old theorems and also generalizing them, making them more beautiful and more powerful. You're going to see that in today's video. The implications of this are actually quite dramatic. It suggests that there's actually a revolution ahead of us here in pure mathematics in the coming century, where we start to rethink what rigor means, what it means to be actually precise and clear and careful about the foundational development of mathematics. Once we take that more seriously, which is what I'm urging us to do, then the possibility of revitalizing and revisiting a lot of theorems comes into focus. Necessarily, we are going to be faced with the perhaps unsettling idea that a lot of the theorems that are out there are really just theorems and not theorems. In other words, if you examine them carefully, the fact that they are pinned onto a real number kind of setup means that they're logically flawed. And they will have to be revisited and rebuilt using a more rational framework if possible. Okay? So there's lots of opportunities that are going to be opening up for researchers, for developers, for people who want to think more clearly and carefully about mathematics. Really the possibility of a lot of interesting development. And a lot of you can take part in this. So over this next coming part of the series, we're going to see more and more examples of opportunities for you to get in there and to start really making interesting discoveries. Okay, so famous formula of Brahmagupta, which motivates this discussion today, is concerned with this kind of situation where we have a cyclic quadrilateral, say A1, A2, A3, A4, and with lengths of sides, let's say A, B, C, and D. Now this happens to be a convex quadrilateral, which informally means that if we choose any 2 points inside the quadrilateral, then the line segment joining them is also inside. That's actually a kind of a problematic definition, so I just want to think about that informally right now. To say that precisely and logically correctly is actually quite subtle, because we don't want to depend on having to check an infinite number of possibilities. The way I just said it involves an infinite number of possibilities. For any 2 points, you have to check that the entire line segment's inside. Okay, so we're going to leave the actual definition of convex and non-convex for another time. It will turn out that the formulation that I'm going to give you today, which is going to be called the cyclic quadrilateral quadria theorem, doesn't in fact require us to be precise about what convex and non-convex means. That will be one of its significant advantages over this classical formulation. All right, so here's Brahmagupta's formula, perhaps in a somewhat novel way, where we write the quadria, which is 16 times the square of the area, as a product of these 4 factors, each of them created by taking sums or differences with these 4 lengths A, B, C, and D. And then Robbins' formula, okay, remarkable modern discovery that there was a similar kind of formula for the quadria of a non-convex quadrilateral, something like this. Also involving the 4 side lengths, A, B, C, and D. But now the combinations are a little bit different. We have A plus B plus C plus D, and then 3 of them with a pair of minus signs in different places. All right, so we have to admit, however, that Precisely speaking, both of these results are logically flawed, in the sense that they require an understanding of length or distance. In the plane, setting up length and distance is problematic, which is why Euclid avoided this issue. In the plane, to define a distance requires a square root. And to create a theory of square roots, we need a prior theory of real numbers. Involved in the idea of a square root is actually an infinite process that never ends. So it's really logically very dubious. Even though practically speaking, if we're happy to truncate this process after a certain number of steps, it can be very useful. But as a concept of pure mathematics, it is flawed, and so these formulas are also necessarily logically flawed. It's important for us to be willing to say that, to be willing to acknowledge that there is a difficulty, even though these are classical and admittedly very beautiful results. We are still allowed to say, wait a minute, there is a problem. There's a problem because of the underlying assumptions that we have a real number system in which this is all happening. And the reality is we don't have a real number system in which it's all happening. All right, so we are going to have to try to find a way of recasting these results in a purely logical, rational way, okay, independent of any prior understanding of real numbers. And we are going to be able to do that. But before I do that, I want to have a look at these two results with the idea of exhibiting some examples, of illustrating what's going on here with some concrete, explicit examples, which will bring to you much clearer the logical problems which are actually underlying these two formulations. Now, it's a consequence of the logical difficulties that pure mathematics is in, that finding explicit and concrete examples for many theoretical situations is often a difficult task for students. We have lots of fancy theories, but when you look for concrete examples where these theories are brought down to earth and exhibited completely so that everybody can look and see what's going on, it can be very challenging. And part of the reason is because if we did look at concrete examples, we would see more clearly the logical difficulties. And I want to illustrate that by looking at some examples relating to the Brahmagupta's formulas and Robin's formulas. Okay. So what would it look like if we tried to exhibit the Brahmagupta's formula in the context of a real number? So let's play along with the usual real number story for just a little while and illustrate this theorem. Well, let's choose a simple circle, the unit circle, equation x squared plus y squared equals 1, and here it is in the xy plane. We want a cyclic quadrilateral, so let's choose 4 points. Okay, 1 point, that's easy, is the point 1, 0. Let's call that A1. There it is there. And now we want to choose some other points, but we want them not to be all just easy points. We want them to be a little bit more general. So how do we get points on the unit circle? Well, the standard story is that we use the cosine-sine parameterization. Most undergraduates have been trained to automatically say that a general point on the unit circle is of the form cos theta sine theta. It's a kind of automatic reflex reaction. All right, so let's do that. So if we want a point, let's say A2, one way of obtaining it is to choose some value of theta. What could be simpler than say theta equals 1? So here is the point cosine 1 sine 1. Well, we have to look that up with our calculator, and it's approximately 0.5403, 0.84107. I've set my calculator, by the way, here to 5 decimal places. So that's the precision level that it's giving me. All right, there it is there. Let's remark that this point is not precisely on the circle, because these are not the exact values of these transcendental functions. There's actually infinite power series that are defining these functions, and we're necessarily chopping off these infinite processes to calculate these transcendental numbers. So already here we're introducing certainly some approximation. This point that I've written down here is not exactly on the circle, although it's reasonably close. Okay, we need some more points. How about cosine 3, sine 3? Let's call that the point A3. And there's its values approximately to 5 decimal places. And how about A4 over here, which is cosine of 6, sine of 6? I remind you that all the way around is 2 pi radians. 2 pi is 6.2 something or other. And here's the values approximately of A4. Okay, so what do we need to do to exhibit Brahmagupta's formula? We need to calculate the side lengths of this quadrilateral A1, A2, A3, A4. And they are, so here's D12, it's 0.95885 approximately, up to 5 decimal places. D23, 1.6829. D34 is 1.9950, and D14 is 0.28224. And how does one get that? Well, one uses the usual formula for distance in the plane, which involves a square root of a quadrant. So the distance between these 2 points, we have to take the difference of these 2 things and square it, add the difference between these 2 things squared, and then we'd have to take the square root of that. Okay. And you will know by now that taking a square root is something that we can talk about, but we can't actually do in completion. So these are just approximations to what we're really having in our minds. Okay, so these are the approximate side lengths. Now what about the area? Or we prefer to think about the quadria. So I remind you the definition of the quadria was 16 times the square of the area. And how do you find the area of a quadrilateral? Well, you use a formula that we talked about last time, which for 4 points looks like this. Okay, so this is the area squared times 16. So the actual area would be this thing here divided by 2. So if we square that, we get this thing squared over 4. We multiply it by 16, we get a 4 out front. And we can evaluate this by replacing x1, y1, x2, y2, etc. by these various values that we've got up here. Okay, so these various values are also approximate, so necessarily this is also going to be approximate. And we're going to get 18.858, approximately. Now, what does Brahmagupta say? Brahmagupta says, in the form that we have, that this quadria should be equal to this product. The product of these 4 factors obtained by taking these 4 lengths and taking various combinations with a minus sign here, a minus sign here, a minus sign here, and a minus sign here. And so we can do that. We can take these 4 lengths that are rated here and we can plug them into here and get our computer to calculate that, and we get 18.857, which is pretty close to 18.858. Brahmagupta's formula says that this thing should be equal to this thing. So what has this shown us? Has it verified for us that Brahmagupta's formula is true? Well, it's certainly given us some confidence in Brahmagupta's formula, because these 2 things are not too far apart. And we can well imagine that Brahmagupta's formula might be entirely correct, and that the difference here is just due to the various round-off errors and the fact that we're not actually completing these infinite processes which are underlying these various operations that were introduced. But it's also possible that Brahmagupta's formula is not entirely true, and that there's some additional term that really ought to be included, which is so small that it's just not registering here. So it's giving us some confidence, but we cannot actually say that we have verified Brahmagupta's formula exactly in this case. We haven't been able to, because we've been using this real number framework, which necessarily introduces, pretty well at every stage, some inaccuracies. Because we're incapable of actually doing real number arithmetic, we can actually only do floating point arithmetic. Our calculators can only deal with decimal expansions up to a certain point. And then after that, they have to truncate or round off. This is why, that's one of the reasons, that you don't see a lot of examples illustrating geometrical theorems in textbooks. Because it's not very convincing if we see a page like this with all kinds of decimal expansions and floating point things around, and the conclusion at the end is that this is approximately equal to that. Well, it doesn't engender the confidence that we would like pure math students to have. And so we have many, many books with many, many theoretical, lovely formulas, supposedly, but a significant lack of really illustrative examples in many situations. Not just elementary geometry. This applies even more so once we get to more advanced mathematics. Okay, I would like to also exhibit a concrete example to illustrate Robin's formula. That's a much newer formula, less familiar, and so it's especially important that we have a go and see whether it actually works or not. So for ease of demonstration, we'll use the same 4 points that we've already talked about, A1, A2, A3, A4, but we'll join them up in a different order to get a non-convex quadrilateral. A1, A2, A4, A3. A1, A2, A4, A3. All right? So, well, first order of business is to calculate the 4 lengths of the sides. D12, D24, D34, and D13. We already have D12. We can calculate D24 is 1.1969. D34 we already have is 1.9950. And we can calculate that D13, this one here, is in fact also 1.9950. And if you think about the geometry of the situation, the way I've chosen those 4 points, you may not be surprised to find that these are the same. Okay, and what about the quadria? Well, it's only an algebraic expression. It's given by the same kind of formula, but we have to now cycle through the points A1, A2, A4, A3. So here's the A1, A2 contribution. Here's the A2, A4 contribution, then A4, A3, and then A3, A1. So we take this whole thing, we square it, multiply by 4. That's the quadria of the non-convex quadrilateral. 16 times the square of the area. And that turns out to be approximately 0.63904. And what does Robbins tell us? He tells us that this should be the same as this product of, again, combinations of these 4 distances, here all with plus signs, and here with these 2 minus signs, and here with these 2 minus signs, and here with these 2 minus signs. So again, we can calculate using these values, and we get 0.63881. And now we compare. Theoretically, these should be the same. They're close, but they're not exactly the same. So again, can we say that Robbins' formula is true? Well, it's approximately true. Can we say that we've actually verified it completely in this one example? No, again, we cannot say that. It's very hard for us to verify concrete examples in a context of real number arithmetic, because there are all those untold decimal expansions out there that we've been ignoring. It's a very problematic business. So we're going to have to find really a better way of thinking about the essential content of these 2 lovely formulas. Okay, so this rather sloppy real number thinking that we've been adopting in these examples has led to imprecision. And let's clarify where the imprecision has occurred. So it occurred, first of all, when we introduced this transcendental parameterization of the unit circle. So cosine theta and sine theta are generally only approximately on the unit circle if we actually calculate these things for some generic examples of theta. We had some confusion over the definitions of convex and non-convex. We were rather vague about that. Of course, the square root that appears in the distance formula introduces approximations. This is a key problem with the very fundamental notion of distance in Euclidean geometry. In fact, Euclid carefully avoided square roots and carefully avoided talking about distances exactly because of this issue. So this claim that distance is a fundamental concept in Euclidean geometry is true only if you regard Euclidean geometry as something different from the geometry of Euclid himself. Then real number arithmetic is an impossibility. It's only something that we can talk about, not actually do. So in practice, all computations are done with floating point. And then we necessarily have truncations and round off and more errors. So a natural question is there a better way? Do we have to do mathematics this way, or is there a step up? Is there a future for mathematics where we don't have to do these kind of games, where we can avoid these kinds of errors and move into a land of complete accuracy and logical correctness? Drum roll. Yes, there is. Of course there is. Let me suggest just a few tips or maybe principles to guide us in a good direction. Apart from, of course, my often repeated statement that it's really the rational numbers which are at the heart of mathematics, so we have to really orient ourselves towards the rational numbers. But you've heard me say that many times already, so you already know all of that. But here are some perhaps new things that I haven't stressed that much. One is that you should have confidence in the algebra. Okay? It will steer you automatically in a good direction. It's a remarkable and beautiful thing. I have no real explanation for why this is so magically true. But it's pretty well always the case that if you do the algebra right, it will lead you to the right way of thinking. We'll see some examples. Second, when faced with several alternatives, either think about finding the special ones or consider them all at the same time. If you have 5 possibilities and they're all staring at you, a natural question is one of these obviously preferable to the others? Is there some one of these alternatives that stands out? Well, if so, then we should treat it specially. But if there isn't, then we should think about all of them at the same time. We should put them all on the same footing and accept them as a happy family. Third, algebra is generally indifferent to order and position. Whether B is in between A or C is in between A or B, or some point is in the convex hull of some other points, these are things that algebra has some difficulty enunciating. Or to put it another way, algebra is largely indifferent to these kinds of issues. So you can expect that working algebraically, there is not going to be a preferred position of 3 points in terms of one being inside the other. Okay. So this is, I think, an important thing to keep in mind. So armed with these insights, we can find the true formulation of the formulas of Brahmagupta and Robbins. And that's what I'm going to show you now. All right, so very exciting. Here is the cyclic quadrilateral quadria theorem. So we're going to attribute this to Brahmagupta, of course, and to acknowledge Robbins' contributions. And, well, maybe I'll give myself a little bit of credit because, as far as I know, I'm the first person to have sort of reorganized the theorem in this form. It was appearing in my book, Divine Proportions, as Theorem 112. Now, it's very possible, however, that this form of Brahmagupta's formula would have been known by other people at some point, maybe earlier. And so I'm quite happy for someone to point out that someone else actually deserves credit for this formulation. In any case, here it is. All right. So if A1, A2, A3, A4 is a cyclic quadrilateral, so it's a quadrilateral whose 4 points lie on a circle, with quadrants is Qij, which is the quadrants between AI and AJ, as I and J run through the various indices 1, 2, 3, and 4. So these are the quadrances. So these are the quadrances. Remind you, the quadrants between 2 points is the square of the difference between the x-coordinates plus the square of the difference in y-coordinates. The purely algebraic quantity. And the quadria A And I remind you that's 16 times the square of the area. And it's given purely in terms of that formula with the x1, y2 minus x2, y1, etc., all squared times 4. Okay, then here is the relation. That the quadria satisfies a quadratic equation. A squared minus 2ma plus p equals 0, where m and p are numbers, and they're given by these formulas. M is this quantity, q12 plus q23 plus q34 plus q14 all squared minus twice the sum q12 squared plus q23 squared plus q34 squared plus q14 squared. And p is actually the quadruple quad function applied to these four quadrants: q12, q23, q34, and q14. So there's actually only 4 of the 6 quadrants that appear. The quadrants from 1 to 2, the quadrants from 2 to 3, from 3 to 4, and from 4 to 1. Only those 4 quadrants appear. Okay, so what you do is you first calculate the quadruple quad function of these 4 things. And this is sort of an ingredient in here. Okay, so when you're calculating this, you can calculate this along the way. Then you have these numbers m and p. You just write down this quadratic equation, and the quadria of the cyclic quadrilateral is a solution to this quadratic equation. So in general, if you're given these 4 quadrances, you should expect there to be, well, depends on the quadratic equation, 2 solutions, or maybe in some special situations 1 solution, or maybe in some situations no solution at all. The 2 solutions correspond to basically the Brahmagupta possibility and the Robbins possibility. Having a convex quadrilateral with given quadrances, or maybe having a non-convex quadrilateral. Both possibilities are contained in this quadratic equation. And it's this general principle that if we have these 2 possibilities, convex or non-convex, instead of trying to separate them and identify them both, we should think about them together. All right, and this quadratic equation does that for us. All right, so this is a reformulation of the Brahmagupta and Robbins formulas. But it's also more than that. Okay? It's more than just a restatement, because it's actually a correct statement. Because it's actually a statement that has ingredients which are all logically defined. We are not relying on a prior theory of real numbers to understand various distances or lengths that appear, because there are no distances or lengths in here. So I think one can fairly say that this is really the first time that these results have been stated in a logically correct fashion. That's a very big statement, which has lots of consequences for other things too. We'll see also later on that this formulation allows us, in fact, to generalize these formulas in many different directions. Okay, so this is a very good formulation for a number of different reasons, which we'll talk about in subsequent videos. But so I offer you this theorem as strong evidence of the utility of thinking rationally and logically and clearly about the foundations of mathematics and geometry.